Hi there, today we'll have a look at the exam of September 2023. As you can see, there are 2 exercise questions and 2 theory questions. For students in electromechanical engineering and health engineering, there is a 5th question that is Matlab related. We can also have a look at the instructions. Have a look at these because they will most likely remain the same for future exams. Before going into the details, let's have a look at all the questions. So this is the first question. This is exercise 1, where you have to use the Laplace transform to solve the differential equation that is shown on the screen with its initial conditions. In exercise 2, you have to use the Z transform to solve a difference equation. That's the difference equation that is shown on the screen with its initial conditions. Pay attention because you have to write the solution in terms of the zero state response and the zero input response. Well, here's the first theory question. You have to obtain the Bibo stability condition for a continuous time LTI system in the time domain. So it's not about poles, right? It's really in the time domain. So first you have to define the concept of Bibo stability, both in words and mathematically. Then you have to illustrate this concept graphically. Next, you need to provide the Bibo stability condition for this continuous time LTI system, as I said, in the time domain. And then in the 4th point, you have to prove the sufficiency of this Bibo stability condition. Well, here's the second theory question, and it's about time frequency duality of the Fourier transform. In the first part of the question, you have to show that when you're given a Fourier transform pair, and here it's f of t and it's Fourier transform, you can find the so-called dual Fourier transform pair, and you have to explain or substantiate your answer. And then you have to explain what is the use of this time frequency duality property. Well, in the second part of the question, you have to use this time frequency duality property to obtain the Fourier transform of a constant signal. And you do this, of course, starting from another Fourier transform pair. So you'll have 2 Fourier transform pairs, and you have to give an interpretation of both these pairs. And finally, in the third part of the question, you have to use this same time frequency duality property to obtain the Fourier transform of a cosine. And then you have to give an interpretation of this result in the frequency domain. Without further ado, let us have a look at exercise 1, where you have to solve the following differential equation using the Laplace transform. If you're preparing your exam, push the pause button and try to do this by yourself. Well, in order to solve this problem or this differential equation, we need to go to the Laplace transform. This is what we do over here. We need the Laplace transform of a second derivative and a Laplace transform of a first derivative. We know that, well, the Laplace transform of the first derivative is obtained by this equation over here. So it's s times the Laplace transform of y of t. So y of t is the primitive of this signal over here, minus an initial condition on y in 0. So if you want the Laplace transform of the second derivative, well, we'll use this equation over here, but here we have second derivative, so we have to use s times the Laplace transform of the primitive of the second derivative, which yields the first derivative, right? And we have to subtract an initial condition on the first derivative in 0. This one we have computed in the line just above, so we need to inject this quantity over here. And if we expand, we have the Laplace transform of the second derivative taking into account the initial conditions. It's quite important, well, to redo this and not switch these two, because otherwise you have made a mistake. You also need the Laplace transform of this signal over here. Well, you know that the Laplace transform of a ramp signal is 1 over s squared. So what we have here is the same, but we have this damping over here because of the function exponential of minus t. But you know that if you damp or you multiply by an exponential in the time domain, well, then you have to shift in the frequency domain. So you know that the Laplace transform of this signal over here is 1 over s plus 1 squared. Let us now continue by regrouping all terms involving y of s on one side. So we have s squared over here, minus 2s over here, and 1 over here. So if we regroup them, we have this second order polynomial that we can factor as s minus 1 squared. The initial conditions we take on the other side, and if we replace by the values that you see over here, you see that this thing here can be replaced by s minus 2. So y of s can be written as a first term that comes from the initial conditions, so it's s minus 2 divided by s minus 1 squared, and here we take this one and divide by s minus 1 squared, and this is this second term y2 of s. So what we have to do for both of them is do a partial fraction expansion. We'll start with y1 of s. We have a denominator that is of the second order, so we need two constants over here, so you need to check this. The one that is easy to obtain is b bar. So what you do over here, you take this one, you hide the denominator, you have s minus 2, and you evaluate it in s is equal to 1. 1 is the, well, the value that makes this denominator 0, right? And you obtain minus 1. For a bar, what you do is take this quantity over here, and you take the first derivative, and then you evaluate it in s is equal to 1. If you take the first derivative, you just obtain 1, so a bar is simply 1. So this is one way to proceed. You might have worked in another way, as long that it is correct. I do not check the results over here, but at the time of the exam, it's always a good idea to put this again under the same denominator and check that you obtain indeed this quantity over here. We can now do the partial fraction expansion of y2 of s. We have a fourth order, so we need 4 constants, and this is indeed the case. Well, here it's again the same thing, right? You take this one, you hide s minus 1 square, so you have this thing over here to compute b, right? And this time the root is in s is equal to 1. It's the same actually. So if you replace, you have 4 divided by 2 squared, so this is 1. For the value of a, you take this one, you take its derivative, and you replace by s by 1. If you do the calculations, you will see that this is minus 1, right? And you can clearly see here that b bar is minus 1, and here b is 1, so these two terms will cancel out if you add these two over here, and you have something similar for a bar and a. They are opposite, so they will cancel out over here. For c and d, well, it's the same kind of idea. We compute d as first, we take this one over here, we hide this one, we obtain this thing over here, and now the root is in s is equal to minus 1. So we have 4 divided by minus 2 squared. So this is 4 divided by 4, so this is indeed 1. And for c, we take this quantity, we take the first derivative, and we evaluate in s is equal to minus 1. If you do this, it's also 1, right? So we can now look at y of s, and we see that what we keep are these two terms over here. As I said, these ones cancel out. So you have a 1 over s plus 1 and 1 over s plus 1 squared. So now it's time to take the inverse Laplace transform. Here you have exponential of minus t times u of t, and here it's the same Laplace transform as we had over here, we have t times exponential of minus t u of t, and if you add, you can write it like this. To check our initial conditions, right, what we need to do is compute the derivative. So we have this one times the derivative of this quantity over here, which is 1, right, and then this one times the derivative of this one. So it's an exponential of minus t, and then don't forget the minus 1, because the derivative of minus t gives minus 1. If we look at the initial condition in y, you have to plug in 0 for t. You see indeed that you have a 1 over here, and for the derivative you have to take this one. This will produce a 1 and this will produce a minus 1, so it's a 0. And as you can see, this checks out with the initial conditions that we had in our exercise. So this concludes, well, exercise 1. Let us have a look now at exercise 2, where you have to solve the following difference equation using the z transform. You have to write the solution in terms of the 0 state response and the 0 input response. As usual, if you're preparing your exam, it's time to push the pause button. Well, in order to solve this difference equation, we have to go to the z domain, right? And we need the z transform of yn minus 1. So it's yn shifted to the right by 1. And here you have something similar, but shifted by 2. And we also need the z transform of this signal over here. So here are the two shifting properties, right? You'll find the details of this in the course, but you can kind of see that this is shifted once to the right, so we have to use the shifting operator z minus 1. What will happen is that if you shift to the right, if you compare with the z transform of the original signal y of n, you'll have y minus 1 appearing in position n is equal to 0. So you have to add something, y minus 1, and then z to the 0. And z to the 0 is 1, of course. You have something similar here, but we have, well, a shift by 2 elements, so we have to use z minus 2, right? Y minus 1 will appear in position n is equal to 1, so we'll have y minus 1 z to the minus 1, right? And what was in position minus 2 will now appear in position 0. So you have to add y minus 2 z to the 0, right? And this is used for this z transform. This is what you have over here, right? Don't forget again the parenthesis. And here we have the z transform of y, but shifted 2 times to the right. This is what you see over here, and again, don't forget the parenthesis. Now we need the z transform of this signal over here. Using the definition of the z transform, it's quite easy to find that the z transform of alpha k u of k is z over z minus alpha. We'll call this f of z, and what we need is the same, the z transform of the same signal, but with the k over here. And we've seen that there is a property that you cannot obtain this z transform by taking this one, differentiating with respect to z, and then multiply by minus z. If you do the calculation, you will see that the result is given over here, right? And we prefer to work with z minus 1, since in our problem here we're shifting to the right, and as you can see, naturally you have z minus 1 appearing, right? So we'll work with the variable z minus 1. So if we do this z transform, this is what we obtain, and here we don't have to forget, of course, the factor 20. Right? So what we'll do now is group everything that has a yz. You have a 1 over here, minus 5z minus 1, plus 6z minus 2, and this you can factor, right? I factored it for you over here. Don't forget at the time of the exam you have to check this, right? Because I often see mistakes, right? Here it's done correctly. If you do the multiplication, you will find indeed this thing over here. You take the effect of the initial conditions on the other side, and then you replace by the initial conditions that you see over here. You will see that these will cancel out, and you'll be left with minus 36z minus 1, and this one we keep, right? We divide by this thing over here. You'll find it at the denominator over here, and we have y of z. We keep the two terms, one coming from the initial conditions and one coming from the input, right? So the first term over here will be the equivalent of the zero input response because it comes from the initial conditions, and this will be what is coming from the input. So it's the zero state response. And of course what we need to do now is to take the inverse z transform to obtain the zero input response and the zero state response. To do this, we'll have to do a partial fraction expansion of both those terms. So if you're preparing your exam, it's still time to push the pause button. So what you can do now is indeed write the partial fraction expansions of the first term and the second term. This is what you have over here and over here. Here we have a second order denominator in z minus 1, so we expect two terms, two constants, and this is correct. And here we have a denominator in z minus 1 that is fourth order, right? So we expect four terms, and this is indeed what we have. Now it's just a matter of computing the constants, right? I'll maybe explain this one because this is quite standard. What we do to obtain this one, since we have this denominator, we hide this one here, right? This is how you obtain this expression, and then you evaluate it in the root, and here the root is in z minus 1 equals a half, right? If you do this, well, you will see that a bar is 36. You can do something similar for b bar, a, b, and d. For c it's a bit more complicated because since we work with the variable z minus 1, it's difficult to use this trick with the derivative. So I've done it differently here. It's easier. And the idea is to put everything back under the same denominator and to write the numerator of this quantity. I've done it over here. So here you find the expression of the numerator, and you know that this numerator should be 20z minus 1, right? And what we'll do here is look at the terms in this denominator that are independent of z minus 1. In this one it's a, in this one b, in this one c, and in this one d. So a plus b plus c plus d is equal to 0. Why 0? Because we don't have an independent term over here. And this computes the value of c, which is 25. Once you have the value of the constants, well, you can plug them in over here and over here. For this first term over here, which corresponds to the zero input response, well, it's quite standard to obtain the zero input response. It's just a matter of taking the inverse z transform, right? For this term it's a bit more difficult because you observe that in the last term over here you have something that is not a known z transform, because you would expect a z minus 1, right? If you have a square here, a z minus 1, if you wanted to have a standard z transform. So you have to use a trick that you've seen probably before. Well, this is what we have here in this last term. What we do is subtract z minus 1 and add z minus 1 at the numerator, and then we split in two terms. We take this one over here, right? This is what you have over here, and of course you see that the numerator will cancel out with the denominator, and then we'll have z minus 1 divided by this quantity squared here. And now this is a known z transform. And here, since this cancels out, you obtain the first term that is also a known z transform, right? So once you have this one, you can split it in two terms that correspond to known z transforms. So if you do that, well, you obtain, of course, this term, and here we have 35. Why is it 35? Well, it's 25 from this one and 10 coming from this one, right? This is this term over here, and then we keep 10 over here that correspond to this term over here. And now you're ready to do the inverse z transform. If you do this, you obtain the zero state response. As you see, I have the zero input response, an expression in n, and the zero state response, an expression in n, and this is really what I need here to answer this exercise, right? If you add the zero input response and the zero state response, this is what you will obtain. And of course, we like to check our results. Okay, so the first thing that you have to do is, well, use this equation, take this term, put it on the other side, take this term, put it on the other side, and this is what you have over here, right? And now we can use this equation to compute y0 and y1, okay, because we don't have access directly to y0 and y1. We have access to these initial conditions in n is equal to -1 and n is equal to -2. But y0, if you plug n is equal to 0 in here, you can compute it, right? So you plug 0 here, 0 here, 0 here, and it's quite obvious if you do the calculation that y0 is equal to 0. And if you plug in n is equal to 1 in this equation, you'll find that y1 is equal to -16, right? So this is simply obtained by the initial conditions and by the original difference equation. And now we have to check that our solution here matches what we see over here. So now we take the solution, we plug in 0, and we compute y0, and again we see that this corresponds. Okay, we have y0 is equal to 0. We do the same for n is equal to 1, and indeed we see that y1 is equal to -16. So we are kind of happy because our solution matches the initial conditions. And this concludes the second exercise. We can also have a look at the theory questions and see what was really expected. For theory 1, we had a question about the Biot stability condition for continuous time, linear time invariant systems. So in the first part of the question, you are asked to define the concept of Biot stability and to explain it in words and mathematically. So for this first part of the question, we really expect what is on this slide, right? So Biot stability establishes that for a bounded input x of t, the output of the system is also bounded. And then of course you have to explain what we mean by a bounded signal. So for instance, a signal x of t is bounded if, well, its absolute value is smaller than a given constant m for all t. This means that the signal x of t lives between the bounds -n and m for all t. For the second part of the question, you have to illustrate things graphically. This is illustrated in the following slide from the course. The system is Biot stable if you take any bounded input x of t. So this is a x of t that lives between the bounds -m for all t for some constant m. Well, this bounded input x of t should produce a bounded output y of t if the system is Biot stable. And again, bounded output means that y of t lives between some bounds -l, right, for all t. In the third part of the question, you simply need to provide the Biot stability condition, and I insist it's a condition in the time domain. You will see that it's a condition on the impulse response of the system. So here's the Bibo stability condition in the time domain. So the linear time invariant system is Bibo stable if and only if its impulse response is absolutely integrable, and this is the expression of the condition in a mathematical form. If the system is causal, well, when you apply an impulse, applied in t is equal to 0, of course the impulse response will be 0 before t is equal to 0. So this reduces to the following expression, right? The minus infinity bound becomes a bound in t is equal to 0, right? So this is the condition for a causal system expressed in a mathematical form. Although this is not the topic of the question, of course a simpler way to test Bibo stability will be to use the Laplace transform of the impulse response, what is the transfer function, and to look at the poles. And of course they should be located to the left of the imaginary axis. And finally, in the fourth part of the question, we need to prove the sufficiency of this Bibo stability condition. Well, let's have a look at this proof for sufficiency. We're given an LTI system with an impulse response h of t. We have an input that is bounded, and we need to look for a condition under which the output will be bounded as well. So we know that x of t is smaller than some constant m for all t, right? And we need to look for a condition under which y of t will be bounded as well. So we need y of t in absolute value smaller or equal to some constant L for all t. Of course, we'll start from the convolution integral. Okay, this is the convolution of h of t and x of t. I forgot here the star for convolution, right? It's a commutative operation, so you can rewrite the integral as follows, right? So now we'll look for the bound of on y of t. Here it is, right? And here we'll use a property. It's given in the beginning of the course, but it's a generalization of, well, the absolute value of a plus b smaller than equal than the absolute value of a plus the absolute value of b, right? You can generalize it even further, right? The absolute value of this sum is smaller or equal to the sum of the absolute values. This is true for real numbers. This is also true for complex numbers, and you can generalize it for functions. Again, you will find this at the beginning of the course. So this is why we can replace this expression here by something that is larger. Okay, so this explains smaller or equal, right? So the bound on y will be smaller or equal to this quantity over here. We have here that x of t is bounded, so of course if you shift it, the bound will remain the same. So this is really m over here. Okay, so we'll replace, and this is smaller or equal to m, so we'll replace it by something that is larger. This is the m over here. And now we can use our property. You can see that if the impulse response is absolutely integrable, you have something finite over here, right? So you'll have something finite over here, and you have just shown that there is a bound on y of t, right? So we have shown the sufficiency of the stability condition. As it mentions over here, it's also possible to prove the necessity, but this is more complicated, and this is why I only ask you to prove the sufficiency. We have shown that if the absolute value of the impulse response integrated from minus infinity to infinity is bounded, then you have proven that, well, the output will be bounded, whatever the x of t that is bounded as well. So we can also have a quick look at the second theory question. This question is about the time-frequency duality of the Fourier transform. So in this first part of the question, you have to show that you can construct a dual Fourier transform pair corresponding to an initial Fourier transform pair, and here it is f of t and its, well, Fourier transform f of omega, and then you have to substantiate your answer, right? And then you have to briefly explain why this time frequency duality property is useful. You'll find the answer of the first part of the question in the following slide. So here you have the initial Fourier transform pair that is mentioned in the question, and you can construct a dual Fourier transform pair as follows. You take the function of frequency, you make it a function of time, and its Fourier transform can be constructed from the original function f of t. You multiply by 2 pi and you replace t by minus omega. So you can construct one Fourier transform pair from another Fourier transform pair. And this might become handy when it's difficult to obtain the Fourier transform of a given function. Remember, there are two methods to obtain a Fourier transform. Of course, you can use the definition of the Fourier transform and make the calculation. Another way is to use the Laplace transform that you all know very well usually, and the idea is there to replace s by j omega, but this you can only do if sigma is equal to 0, so that's the imaginary axis is in the region of conversion of the Laplace transform. So to prove this property, we'll start with the inverse Fourier transform. So we have f of t, right, and capital F of omega, its Fourier transform. They are linked, of course, by the inverse Fourier transform. F of t is the inverse Fourier transform of capital F of omega. What we'll do here is use a change of variables. We'll replace omega by rho to obtain this expression over here. And now what we'll do here is replace t by minus omega and multiply by 2 pi. If you plug this in here and in here, you have 2 pi f of minus omega, and then you replace t by minus omega and you obtain this expression here. So what we'll do is do another change of variables. We replace rho by t, and what appears here is the Fourier transform of capital F of t. So we have constructed another Fourier transform pair. So capital F of t, and its Fourier transform is 2 pi. You take the original function of time and you make it a function of frequency, and you don't forget the minus sign over here. In this second part of the question, you have to use the property that we have just proven to obtain the Fourier transform of a constant signal. We'll see that we'll start from the Fourier transform of a delta function. And then you have to give the interpretation of both Fourier transform pairs. Well, the answer to the second part of the question can be found in the following slide. We start from the following Fourier transform pair. So we have a time function and its Fourier transform. The time function is simply an impulse, Dirac impulse times a constant, and its Fourier transform is simply the constant a here that multiplies the delta function. Where does this come from? Well, to obtain this Fourier transform pair, we can simply remember that the Laplace transform of the delta is 1, right? So the Laplace transform of this function is simply a, and what you have to do to obtain the Fourier transform is replaced S by j omega, but here you have a constant, so it remains a constant. And you can do this because, of course, the region of convergence of the Laplace transform with delta, which is a 1, right, is the whole imaginary complex plane. So, of course, the imaginary axis is in the region of convergence. So you can use this way of computing the Fourier transform that is based on the Laplace transform. So we start from this original Fourier transform pair and we use it to construct the dual Fourier transform pair. So this is a function of frequency, okay, and we make it a function of time, right? So now this is our function of time, which is a constant a, and its Fourier transform can be obtained from the original function of time. We have to multiply by 2 pi, and we have to replace t by minus omega. But this quantity here is equal to this quantity over here, and this is simply because a delta function is, of course, an even function. So delta minus omega is equal to delta of omega. So now we can have a look at the interpretation of both these Fourier transform pairs. This is here the Fourier transform of a delta, and you can see that you have something that is constant over frequency. Yeah? And the interpretation is that really a Dirac impulse contains all frequencies with the same amplitude. And of course, this makes it impossible to create in practice. And this is a function that we use as a mathematical tool. And here we have the Fourier transform of a constant function over time, and we see that it's a delta over frequency. So this means that the constant signal only contains one frequency, and of course it's the zero frequency. Finally, we can have a look at the third part of the question, where you have to use this duality property to obtain the Fourier transform of a cosine signal and then give the interpretation of the result in the frequency domain. In order to find the Fourier transform of a cosine, we'll first need to construct a Fourier transform pair with, at the right hand side, a cosine. Right here we have a function of frequency, and this function over here is the Fourier transform of this time domain signal over here. So how can we find this? We remember that the Fourier transform of a delta is 1. But if you shift the delta, what you'll have is the original Fourier transform, and you'll have this complex exponential appearing. So here we shift to the left, and there we shift to the right. So we have the appearance of these two terms over here, and we remember that you can use these two terms to, well, construct a cosine. Since we don't have the divided by 2 over here, we have here the factor 2 appearing. So this is really Euler's identity. So now we can use this first Fourier transform pair and use the time frequency duality property to construct a dual Fourier transform pair, right? So what we'll do over here is make this a function of time, right? So we replace omega by t, right? And the Fourier transform will be obtained by considering this function, multiply by 2 pi, and replace t by minus omega, right? You remember that the delta is an even function, so this thing here you can rewrite it as follows, right? What we'll do is replace in this equation here tau by omega 0, and then we obtain the dual Fourier transform pair. Here a function of time that involves the cosinus omega 0, and here it's Fourier transform. Let us now have a look at the interpretation. So this is the result that we had obtained. If you write it in terms of the frequency f0, this is what you obtain. And then you can clearly see the interpretation. Remember that a cosine, and there is even an animation in the course, can be constructed from two phasors, one turning counterclockwise at the frequency f0, this is this one, and another one turning clockwise, and this corresponds to the frequency minus f0, and both phasors have an amplitude of a half. And this is clearly what you see here in the amplitude spectrum of a cosine.